the talk, and you should receive a notification now to allow the recording, and then all the participants will be muted, but if you have questions, just type them in the chat during the talk, and I will monitor those for you. And for all the registered participants, the recording as well as the slides will be available after the talk. So today we have Dr. Nicole Rassar from Penn State Statistics. Dr. Rassar has a lot of research interest in fMRI data and empirical likelihoods, but today she's going to talk about a different topic, which is of interest to many of us. So I'm going to stop sharing my screen and allow Nicole to share her screen.
Okay.
Thank you, Nicole, for agreeing to give us a talk.
Sure. All right. Share and make this full screen. Okay. Can you see my slides?
Great. Yep.
Okay. All right. Well, thanks for inviting me and for coming this afternoon. So yeah, I'm going to talk today about a sort of cluster of topics that I've been interested in for a while, which is capsulated in the title here: open science, reproducible research, and statistical reform. Okay. Right. So, sorry, can I get rid of this? Right, never mind. All right, I'm just going to go. So I guess the first question that I would start with is there a reproducibility crisis? And I'll give you some evidence for this, for the existence of a reproducibility crisis. Lots of people have talked about this, and it's worth, I think, examining the question. So in 2016, Nature did a survey of close to 1,600 researchers and asked whether they thought there was a reproducibility crisis in their field. 52% said that yes, there's a significant crisis. 38% said a slight crisis, and only 3% said no crisis. We've also recently done a survey here at Penn State about open science, and one of the questions we asked was Penn State researchers whether they thought there was a reproducibility crisis in their field, and 20% said no crisis, and the rest said either they didn't know or they thought that there was a significant crisis. And so there's at least some evidence that yes, there's some kind of reproducibility crisis. There have been high-profile failures in the social sciences of replication of studies, and I'll talk a little bit about one big project, which is the Center for Open Science Reproducibility Project on Psychology, but it's not limited to the social sciences, so those definitely they've gotten a lot of attention. Other fields have problems as well, and again, I'll talk a little bit about this project from the Center for Open Science, a reproducibility project about cancer biology. Okay, and just moving forward, I want to make clear what I mean by reproducibility and replicability, because those terms are used, and they're used in different ways in different fields. And so what some areas call reproducibility, other areas call replicability. I'm going to use the definition that was given by the National Academy of Sciences a few years back. So reproducibility in their definition is the following. So if I give you the original data and I give you my code, can you get the exact same results as I get? So can you reproduce the original results given the data and the code? Some people call this computational reproducibility because it's really focusing on that computational aspect. And you'd think that that would be sort of an obvious, easy thing to attain, but in fact, it's not. There are many failures even at the level of this kind of basic reproducibility. Replicability is if you have different but similar data, so maybe you're trying to study the same or a related experimental question, you collect your own data, so you're not using my data, you collect your own data. Does a different researcher get similar results to the original? So maybe, different subjects, slightly different circumstances, but we get consistent results. So this replicability has to do with consistency or generalizability of scientific results. Okay, so both of these are of interest, and both of these have had problems with them. Okay, so I said I want to talk a little bit more about this reproducibility project in psychology. So this was pretty high profile because it was not very successful. So what the Center for Open Science was trying to do in this project was they were conducting replications of 100 experimental and correlational studies published in 3 leading psychology journals. And this is a summary just of some of their findings. So almost all of the original studies, 97%, had what were called statistically significant results. I'll talk more about that notion later on in the talk. So roughly speaking, p less than 0.05, so p-values less than 0.05. And this shouldn't surprise because, as we all know, one of the criteria almost for getting something published is that you have a quote unquote positive finding. So you have to have something that is statistically significant in this way. And so it's not surprising that almost all of the original studies had statistically significant results because null results are hard to publish. Only 36% of the replications had statistically significant results. Okay. More interesting, perhaps, is that the effect sizes were not the same. About half of the original effect sizes were in the 95% confidence intervals of the replication effect size. So if you think about, you do the replication study, you compute effect sizes for the replication, you compute confidence intervals, and then you look to see if the original effect sizes are included in those confidence intervals. Only about half of them were. About 40% of the effects were subjectively rated to have replicated the original result. And the replication effects were smaller. In fact, on average, about half the magnitude of the original effects. And so you sort of see that it's kind of mixed, right? It's not like a complete disaster, but it's also not a very strong result in terms of the replicability that they were trying to attain. And there's been back and forth in the literature about whether they were really replications, whether the conditions were fair, and so on and so forth. I'm not going to get into those details unless people are interested in learning a little bit more. The cancer biology project was interesting as well. So this was a little bit later, maybe about 5 years after the psychology project. And here they were attempting to replicate 193 experiments from 53 different papers that had been published. And what's interesting to me, what's interesting about this project that we didn't see in the psychology one was that in their recounting of this particular reproducibility project or replication project, the researchers also talked about the challenges that they encountered in trying to do the replications. And so here's some of the challenges they found. Almost none of the experiments had open data. So that meant that to get the data, they had to contact the researchers. So they weren't publicly available. None of the studies had completely described protocols. So obviously, if you want to replicate a study, you need to have a well-described protocol so that you can know what the original researchers did, so you can try and do it in your own lab. But none of them had completely described protocols. When they contacted the authors to get information, about a third of them were either unresponsive or unhelpful. And about 2/3 of the studies actually required modification to be able to complete them. So they couldn't just run with what had been originally done. So this is even before we get to the results themselves. These are just the problems that the researchers had in even attempting to do the replications. If we look at the results themselves, again, not super successful. So they were able to complete 50 replication experiments from 23 papers. So they generated data on replicability of 158 effects, not all of the ones that they were originally interested in. Here, the replication effect sizes were a lot smaller on average than the original findings, 85% smaller on average, in fact. About half of the effects replicated successfully on more criteria than they failed. It's again language from the report, so you'd have to go in and dig more closely to see exactly what they mean by that. And then original positive results, so again, sort of statistically significant, were half as likely to replicate than original null results. So if we take all of this together, and there's a lot more. These are just two big examples, but there are a lot of other studies out there looking at replication, and overall, it's just not an encouraging picture. It's very hard to replicate for a variety of reasons, some of which have to do with the challenges and the barriers that the project for the cancer biology found. Just, the details are not there and authors are not necessarily helpful. So what do we do? Okay, so I want to go back to the Nature survey because there's a lot of other interesting information in there as well. So one of the other things that they asked the researchers about was whether they had ever attempted to do a replication study. And so across the fields, and the fields that were represented in the survey were chemistry, biology, physics and engineering, medicine, earth and environment, and then another category of other. So across those fields, more than half of the researchers reported that they'd failed to replicate results from someone else's study. So they looked at someone's report, published journal article, they tried to replicate the results, they were unable to. Interestingly, also, not more than half, it was a little bit less than half, and it varied quite a bit from field to field. They also reported failures to replicate their own results. Okay, so you try to reproduce in the lab what you did, and you don't, or maybe what your lab mate did or whatever, and they can't even always do that. It's not very back in 2016. I think it's becoming a little bit more common now, but back in 2016, it was not all that common to try to publish replication studies because journals are just not interested in them. But interestingly enough, successful replications were more published than unsuccessful replications. So if you've managed to replicate the results of somebody else, then you had a slightly better chance of getting it published. If you didn't replicate the result, then it was harder to get published, which may or may not be a desirable thing, something to think about. When they asked researchers why they thought that results hadn't replicated, so this is the percent reporting that these always or often contribute to failures to replicate. And I've selected, there were about 10 in here. So there's a couple that I left out because they were not directly relevant to the kinds of things I want to talk about later. But I think it's interesting, or I found it very interesting to look and see what were the reasons that researchers cited for failures to replicate. So we have selective reporting was cited by about 70%. So that means that not all results are reported. And this is obviously something that's going to make it harder to replicate if not everything's out there. Pressure to publish, low statistical power and poor analysis, not replicated enough in the original lab. So the original lab wasn't careful enough in doing the work and making sure that it replicated before they published. So that makes it harder for other people to replicate their work. Method and codes being unavailable, poor experimental design, the raw data not being available. And about 40% said that fraud could be a reason for why studies fail to replicate. So from this, I saw a few themes emerging. Okay, first of all, some statistical problems. So these are things like selective reporting, low power or poor statistical analysis or poor design. Openness problems. So here we have the methods and the code not being available or the data not being available. And then what I'm going to call incentives problems, which are things like pressure to publish and fraud. And I'm going to talk about these three, but I'm going to talk about them in the reverse order from how I have them listed here. So I'm going to start with incentives, and then I'm going to move on to openness. And then at the end, I'll talk about statistical issues. So the incentive problem, I call the tale of the QRP. So QRPs stands for questionable research practices. This comes from a paper by John and colleagues that was published in 2012. They include in their list of questionable research practices, they include fraud, but they're not the same as fraud. So in my discussion, I'm going to take fraud out of the picture because questionable research practices are things that we can look at and say, you probably shouldn't do that, but they're not done maliciously necessarily or with intent to deceive, whereas fraud is obviously with an intent to deceive. But these questionable research practices can undermine the replicability of research, and they do stem in part from misaligned incentives and pressure to publish. So here are examples of QRPs. And I said, I've left out fraud, which is in this list as well. But if you look at the list, you can see that many of them are statistical, right? So failure to report all outcome measures in a study, deciding whether to collect more data after looking to see if the results were statistically significant, failing to report all conditions in a study, stopping collecting data earlier than planned because one found the result you'd been looking for, rounding off p-values so that you get the statistically significant result, selective reporting of studies that worked, deciding whether to exclude data after looking at the impact on results, and so on and so forth. So if you look at this list, and you might look at it and say, well, we do those things. And in fact, in our statistics classes, we were maybe taught to do some of these things, right? So this is why I say that it's not fraud. It's not done with an intent to deceive or to do something wrong. And there are sort of valid ways to do some of these things. So for instance, deciding whether to collect more data, that's a sequential analysis potentially, but that's not necessarily what people do. Stopping collecting data earlier than planned. Again, maybe that's something that could be statistically valid, but the way that they're carried out typically ends up being questionable because they're not sort of taking the whole statistical picture into consideration. And so these are things that people will sort of routinely do. And but John and colleagues considered these to be questionable. They did so in their paper, they did a survey of psychologists, and they found that a high percentage of psychologists admit to these practices that I showed on the previous slide. They think that their colleagues use them as well, and they generally think that they are justified. So they don't think that they're doing anything wrong, and they think that this is an okay thing, that these are fine practices to do, that they're justified. A follow-on paper in 2015 by Fiedler and Schwartz questioned the findings. In particular, they questioned the percentage that are actually using these questionable research practices and whether some of them were actually questionable at all. Later, a little bit after that, there was a sort of a survey, a systematic survey of more than 60 studies of questionable research practices. And this paper by Banks et al. 2016 suggests that QRPs are in fact very common. And so there's still some, again, back and forth within the literature about how common these practices are and whether they really are serious or not, whether they are really a problem. There's other things that we could talk about here under sort of incentives that lead to questionable practices that come about because of pressures to publish and sort of not the best of incentives built into our system. So these are things like p-hacking, which are kind of related to some of those questionable research practices. So this is where you basically slice and dice and do all sorts of different analyses until you can find statistically significant results, and then those are the only ones that you report. Related to this is undisclosed researcher degrees of freedom, which is the same idea that you have lots of different choices in your analysis, and you can, again, only report the ones that lead to positive results. Garden of Forking Paths is another take on this same idea. Harking, which is hypothesizing after the results are known. So you look at your data, and then based on what you see in your data, you do a hypothesis test, and you act as if this was something that you had planned to do all along, but you really came up with the hypothesis because of looking at the data. So again, obviously this messes up your type 1 and type 2 error controls. And so these are all things that are problematic. And bottom line is there are incentives built into the system for publication, for funding, and so on to get positive results or statistically significant results. And at the moment, there's not much incentive, if any, towards null results. And so if that's the situation that we're living in, and to get funding and to get our work published, we need to get positive results, then of course, we're going to make sure we get positive results. And again, not necessarily even consciously or maliciously, it's just that's the way the incentives go. Okay, so here comes open science. According to Wikipedia, and this, I don't usually go to Wikipedia, but this is a pretty good definition of open science. It's the movement to make scientific research, and this includes publications, data, physical samples, software, everything that has to do with scientific research, and its dissemination accessible to all levels of society, whether they're amateur or professional. So it's basically a movement for increased transparency in research, and partly as a way of increasing reproducibility and replicability. It has other goals as well, but this is a major goal of the open science movement, is to have this transparency, make it clear what we've done, put it all out there, and then the hope is that this would increase in reproducibility and replicability and put us on a better path. So what is open science? I'm going to show here a couple of schematics just to kind of talk through some of the ideas about open science, and really open data, open materials, and open access are what people will often call the pillars, the three pillars of open science. So open data is as it sounds. You should make your data open. Open access refers to how you publish your studies. Open materials is things like code, that those should be open as well. I'll talk a little bit more about each of these. But there are other things as well that some people include. So for instance, pre-registration is one, which I'm not going to go into, but if people are interested in the Q&A, I can talk about pre-registration a little bit more. Open educational resources. So this is making your teaching material open and free, ideally, for students. And then citizen science is often included in the open science movement as well. So this is one schematic. Here's another open science principle. So you can see here open data. So again, this idea of sharing your data, open access, we've seen before as well, publishing, and open methods. But this group includes a few other things. So open resources, this is, again, the open educational resources, but a little bit broader than just teaching materials. Open source is, again, this idea of code and analysis. And then, interestingly, and this is sort of, again, trying to shift incentives a little bit, is this idea of open peer review. You know, a lot of the peer review that we do now in statistics anyway, a lot of it is double blind, which means that the reviewers don't know who wrote the papers, the authors don't know who the reviewers are. But in my work as an editor and associate editor, I have been starting to encounter referees who sign their reviews. They're like, I'm not going to hide behind the blinding. I'm going to own my comments, as it were. And again, open peer review is something that's starting to gain some traction. Okay, so I said I was going to talk a little bit more about code, data, and papers, because this is sort of, I think for us as researchers, this is probably like things that are most tangible. So open code is not enough to share. It has to be actually usable. And that means that you need to annotate your code carefully, and what are called software dependencies need to be made clear. So if your program relies on a particular version of R or Python or whatever, that needs to be made clear as well. You should put your code, again, this open code principle says you should make it usable, and it should be freely available on sites such as GitHub. But just posting it is not enough. And my students have encountered this frequently, and maybe yours do as well. That they want to use someone else's code that's been published in a paper because they want to try some method, they want to compare their method with their method, whatever it is. And they get to their GitHub page, they find the code, they try to run it, and it doesn't work. So then they contact the authors, and maybe the authors answer, and maybe the authors don't answer. A lot of times when the authors answer, it's, oh yeah, you need to use this version or that version, or it's not, you need this other piece of thing, and it wasn't clear. Okay, so just having the code out there, if it's not actually usable, is not that helpful. Open data means that to the extent possible, you should share your data freely. And this is starting to become a requirement. NIH, for instance, has new data sharing policies coming into place. And again, they don't say that you have to share. There are obviously some types of data that you can't share for particular reasons, but you have to have a plan for managing and sharing the data. And the plan the plan can be, I can't share these data because of reason X, Y, and Z, but you do have to have an explanation. One of the important things that comes out in terms of open data are the so-called FAIR principles, which means that the data should be findable, easy to find, accessible, easy to get to, interoperable and reusable, basically meaning that if I want to combine a data set with another data set, that should be easy to do. If I want to analyze the data for a different purpose than what you, the data collector or the data generator, analyzed them for, I should be able to do that as well. So basically, if the data are out there, then other people should be able to use them for their purposes as well. Open papers means, again, publishing open access, which is a little bit controversial. But you don't have to publish just in open access journals. You can make your work open access in a variety of ways. And for instance, you can use preprint servers to make your work available. And there are other things that you can do as well. If you don't want to publish in an open access journal, or you don't want to pay, right? This is one of the barriers to publishing your work open access in a sort of a regular journal, is you have to pay to do that. And you might not want to, you might not be able to. And so there are other ways that you can do that. And Penn State has a variety of methods for making that more doable. Okay, so we've talked about incentives, we've talked about openness. I want to now talk about the reproducibility crisis and statistical reform. So that last piece that I mentioned coming off from the survey, the Nature survey. So p-values. I've talked a little bit about statistical significance. Here we have it in a little cartoon version. So we have on the left side a variety of different p-values, on the right side how they tend to get interpreted. So, you have a small p-value that's highly significant, and then it's significant. And then, if you're just a little bit above 0.05, then people start saying it's on the edge of significance, highly suggestive, significant at a different level than what I originally picked. Or if it's just too high, hey, you've got a subgroup analysis that maybe you could do instead. This is a cartoon and it's meant to be funny, I guess it is kind of funny, but you can find statements like these in the published literature, and you don't have to look too hard to find them. And so it's a problem. People misunderstand p-value. People misunderstand significance testing, what it's meant to do and what it's not meant to do. And so we get into this situation where people don't understand p-values necessarily, and they indulge in what some people call significance chasing, which again, you want to get those quote unquote positive results so that your papers can get published, you can get funding. But when you do that, this leads to a lack of reproducibility and a lack of replicability, or it can. So definitely abuse of statistics is part of this crisis. Hopefully you can see this cartoon to the end. So here we have on the y-axis, the stat exam grade, on the x-axis, the scream loudness in decibels, and we have 3 data points. Beta, our slope is 1.94, p-value 0.586. Oh, it's not significant. Oh, we need more data. So, each one yells into the mic a few more times, so we get more data points, and now same slope, same general picture, but because we have more data, suddenly our results is significant. Maybe there's a problem here. This is a QRP. This is an example of a questionable research practice. We're collecting more data till we get the result that we want. We're abusing statistical testing. We're significance chasing. Again, this can lead to lack of reproducibility and a lack of replicability. Doesn't have to, but it can. Here is another example of, again, this is from a published paper now, this time, not a cartoon. This is a real published paper, misunderstanding of what a hypothesis test is about. So on the x-axis here, we have age less than 40, age greater than 40. Along the y-axis, we have the ages. And so basically, these people did a test of significance to see whether there was a difference in average age between people that were less than 40 and people that were greater than that and older than 40. And they found a significant result. And this appeared in a paper. Okay. So there's some problems here. But this is not new. So if you've sort of been around in statistics and areas of application for a while, you'll have heard these kinds of conversations. In fact, go back 100 years, to some of the pioneers of statistics, and you can read them talking about issues around p-values and issues around statistical significance. So I've got a couple of quotes here. I'm not going to read through them all. I just want to highlight these by Fisher. It's convenient to take a point as a limit in judging whether a deviation is to be considered significant or not. If 1 in 20 does not seem high enough odds, we can make it at 1 in 50 or 1 in 100. Kramer says this is a conventional terminology. Fisher, one of the originators of this testing ideas, he interpreted p-values in various ways. So 0.05 to 0.1, sometimes he thought this was important, sometimes not. And significantly, when he used the word significant, he didn't mean it necessarily in the way that it's come to be used. He meant it more like something that is worth following up on. So is the effect worthy of more study? And so that's really what he meant by statistically significant. And those p-values, the sort of smallish p-values, really should be context dependent. And this is a longish quote, but I think it's worth kind of reading through and thinking about. So the calculation, he says, is absurdly academic. For in fact, no scientific worker has a fixed level of significance at which from year to year and in all circumstances he rejects hypotheses. He rather gives his mind to each particular case in the light of evidence and ideas. Further, the calculation is based solely on a hypothesis, which in the light of the evidence is often not believed to be true at all, et cetera, et cetera. And so here Fisher is basically saying we should not be using one level of significance, an alpha level, for every circumstance, for every study, but you should think about your particular context and your particular hypotheses and frame alpha in terms of those, which is not what we do. What's happened? So these early statisticians, and there are lots of other quotes that I could pull on, this p less than 0.05 has become entrenched in many areas of science. It's basically become the default level of statistical significance. And in part, it's a result of understanding the two main approaches to hypothesis testing. So Fisher, I've already mentioned, had a testing approach. Neyman and Pearson had a different testing approach, and they were emphasizing different things and they used different pieces. But what we've got now today is sort of a blend of the two of them. So Fisher said, you set your null hypothesis, you compute a p-value, and based on the p-value, you assess whether you want to do another study. So under Fisher's framework, you don't need an alternative hypothesis. You don't consider error rates. So there's no type 1 error, type 2 error, and there's no thresholding of a p-value either. You just compute it, and then you look at it, and you decide based on that whether you want to do something else. The Neyman-Pearson paradigm says you set a null and an alternative hypothesis, and you set your acceptable levels of type 1 and type 2 error in advance. And then once all of those pieces are in place, you compute it. Everything is fully determined. So then you just need to compute your test statistic, and you see if the test statistic value falls into the rejection region, which is defined by all the components of the test. So under the Neyman-Pearson paradigm, you do not need a p-value. Okay, so we get the p-values from Fisher, and we get the thresholds from Neyman-Pearson, but the two of them actually don't exist in the same testing framework. And so we've got this weird situation where we're not doing exactly what Fisher said to do. We're not doing exactly what Neyman-Pearson said to do, and yet we're still trying to draw scientific conclusions. Again, this is not new. If you do a Google search, you will find many, and I do mean lots, published editorials and papers in a wide range of disciplines, ranging from the social sciences, biology, everywhere, basically deploring the use of these arbitrary p-value thresholds and outlining problems with his approach. So this has been something that's been known in terms of both the inference and the implications on our ability to trust the results that we see in the literature, which ties now into notions of replicability and reproducibility. And there are publications from the early 2000s. There are publications from the 1990s, from the 1980s, from the 1970s. You can go back and back and back, and you can find these papers. So, and there have been many attempts over the years to try to reframe the discussion, and mostly they haven't been successful, or they've been of very limited impact. So why are we doing this again? and what has changed this time around, if anything. So I would argue that we're living in a time of a paradigm shift. Again, I mentioned earlier, I talked through these high profile replication failures. So really awareness of the fact that a lot of the science is out there maybe doesn't replicate. So how much can we trust it? There's awareness now of these questionable research practices, again, because people are calling attention to them. And there's the open science movement. So maybe right now we're in a time where circumstances are converging that in such a way that they're going to enable statistical reform. Maybe. So what's been going on the statistics side? So in 2016, the American Statistical Association put out this so-called statement on p-values, which had 6 principles, and here they are. Again, I'll leave this up just for a second so you can see them. I'm not going to read through all of them, but I would just highlight a few. So the first one, p-values can indicate how incompatible the data are with a specified model. The second one has to do with common misunderstanding of a p-value. P-values do not measure the probability that the studied hypothesis is true. This is a common misconception that a p-value gives you the probability that the hypothesis is true or not true. That's not what it does. Here, look, number 4, relating to open science, proper inference requires full reporting and transparency. This is an open science kind of ideal. And then, I guess the 5th one, a p-value or statistical significance does not measure the size of an effect or the importance of a result. So this was published in the American Statistician, where I was editor at the time, along with an online discussion. So this was a statement that was created by a committee of statisticians, not all of whom actually agreed with the final statement and the precise wording and principles. And so when we published the statement in the American Statistician, I invited all of the committee members to write basically online supplements discussing their agreements and disagreements. And most of them actually chose to participate. So you can find that on the American Statistician website, I guess, if you go back and dig to 2016. A few years later, there was a special issue of the American Statistician. Again, this was in 2019. I was no longer the editor at that point. So this was a different editor, but I was a guest editor for this special issue. And basically we invited, again, the whole statistical community, lots of other people to come up with their ideas, submit papers. What should we be doing to move forward? So there are different philosophies about what we should do. Here I've kind of listed in what I would say most extreme to least extreme, the types of proposals. So the most extreme is to ban p-values and everything to do with them. So that's hypothesis tests and all of that stuff, to ban them altogether. There was one psychology journal that actually took that step and said, we don't want to have anything about null hypothesis significance testing in our journal, and that includes p-values, includes t-tests, f-tests, do other things instead. So that's a very extreme position. This Wasserstein et al. Was our editorial introducing the special issue, and this was our stance. We said, keep p-values, but avoid the use of thresholds and declarations of statistical significance, which I guess in the scheme of things is a rather radical proposal. And that's where we sort of synthesizing things from the special issue and the various opinions that people brought seemed to be, it's not a consensus because nobody's ever going to agree on everything, but that seemed like a reasonable position to take based on what we were seeing from the different papers in the special issue. Another proposal is to keep p-values, but change our default threshold for statistical significance. So 0.05 is what's common in the field now. Benjamin and colleagues and 72 people were co-authors on this paper said, well, 0.05 is too high, so make it lower, 0.005, and then we'll have fewer false positives, and so things should, for instance, replicate better. Another proposal, sort of harking back to Fisher's original ideas, again, keep p-values, but take your significance threshold according to circumstances and context. So this is called justify your alpha. Again, lots of people signed on to as co-authors to this proposal. So a variety of ideas about what to do. And then sort of least radical, I'd say, is to keep the status quo. So keep doing what we're doing, but do a better job of educating our students, do a better job of educating scientists and the public. So this is on the philosophical side. In terms of methodology, what to do. So there's different suggestions here as well. And not going to go into details, just want to kind of give you a flavor of the kinds of things that people are thinking about. So some people suggest moving to a Bayesian analysis instead. So Bayes factors, for instance. One interesting proposal that I sort of like is to use what's called an S value or Shannon information or surprisal, where this is just taking minus log 2 of the p-value. So the way that you can interpret this is like how much information, how many bits of information do you have? And the work on the S value is framed specifically in the context of if you're flipping a coin and you observe how many heads in a row. So a p-value of 0.05 is 4.3 bits. So that's like seeing 4 heads in a row. Is that really surprising? Would you think that the coin wasn't fair if you saw 4 heads in a row? Maybe you would, maybe you wouldn't, but that's a way to think about the type of surprisal that is captured in a p-value of 0.05. And then there are other things you could look at, something called false positive risk, something called second generation p-values. If you look in the special issue of the American Statistician, which is available online, open access for everybody forever, that was the deal we made with the publisher. You can find the suggestions, other suggestions. You can read all of the articles of the special issue. And other people in the years since have started publishing other ideas and other proposals as well. So now this has become an area of some interest in the statistical world. Like what other things can we do if we're not going to stick with the sort of traditional ways of doing things? Okay, so some take-home messages, I guess, from the special issue. So as I said, there's many alternatives that are offered in that special issue. Personally, I don't think that there's going to be necessarily a simple one-size-fits-all solution, and it's very possible that different disciplines will arrive at different best practices, okay, and that's fine. But whatever direction you end up going in, if we think about the reproducibility crisis, the replicability crisis, things coming from open science, I think there's still some principles that any solution should adhere to. So in our editorial, we define what we call the atomic principles. So here's the letters are highlighted: A, T, O, M, I, and C down here at the end. So A is to accept uncertainty. The p-value is a random variable, so it's also going to have noise attached to it. So its specific value is not as important as sort of the general trends that it's showing. In line with the open science movement, to be thoughtful, open, and modest. So report what you've done, report more information, not less information, and recognize that one study does not present a complete picture. Related to that, we want to avoid exaggerated claims in either direction about the importance of an effect or the lack of an effect. And we really want to focus on the implications of our estimates and our intervals. Like, what do they actually mean for the science? Not just whether they hit some threshold or didn't, okay? And then, of course, the hardest is, so that's atom coming from the first 2 points. Institutional change is the atomic. That's what makes it atomic. And because it's basically demanding that there needs to be institutional change at the level of journals and the levels of funding agencies. The incentives, even for things like promotion and tenure and hiring, sort of need to change. And this, again, ties up very nicely with direction that the open science movement is moving in as well. So I want to sort of emphasize, because this, I think, gets misunderstood and quite a bit, that the problem is not just with the p-value, okay? Or it's not with the p-value per se. If people understand p-values and use them properly, that's fine. Problem, of course, not everybody does understand the p-value, and it's a sort of a very misunderstood concept, but the problem is not with the p-value. The problem, and where we start running into these bad incentives that can then lead to questionable research practices that can then lead to problems with replicability has to do with thresholding of a statistical measure. If I move to Bayes factors, but then say, well, I have to get a Bayes factor of 10 or 15 or 20 or whatever it is to believe the result, I've got that same thresholding problem, and I'm going to still be prone to those same issues of potentially questionable research practices to get to that level of Bayes factor or whatever it is. So it's the thresholding, that bright line thresholding, that's going to lead to those problems. A question that I like to, that I and my colleagues like to ask is, if I give you an effect size and I give you measure of uncertainty of that effect size, and I give you a p-value, and I give you some good data visualizations, what do you get in addition by attaching the label of statistically significant that you didn't already have from all that other information that I've given you? So if I tell you all these other things, I think you have the information that you need, and just attaching a label to it doesn't give you anything substantively more than what you had before. And then again, as I've kind of talked about a little bit already, if we misinterpret the tools or we use them in situations for which they weren't originally suited, or they're not meant to be used, that's going to muddy the waters further. So just kind of looking ahead a little bit and pulling pieces together, I think what's happening is in the past few years, there's been, I feel like there's been a shift in how scientists think about scientific practice and how they think about statistical practice. And this is coming from my conversations with scientists, of course, those who choose to talk to me about these things. So I realize I'm getting a biased view, but I think there has been a shift. Open science is definitely becoming more prevalent. It's seen as one solution to the reproducibility crisis because, again, it's emphasizing more transparency and complete reporting. It's emphasizing sharing of data and code and methods. And this is what the statistical reform movement is also aiming for. A little bit more controversial maybe for some people because it kind of leaves us with uncertainty about how to move forward. But our atomic principles do align with the open science philosophy, recognizing that institutional change is hard. However, I think that's sort of my ending statement is a little bit pessimistic. I know institutional change is hard, and this is a conversation that's happening in the open science world as well as the statistical reform world. But I just wanted to kind of use this opportunity to bring some of these ideas to your attention if you haven't seen them before. And as I said, I'd be happy to take any questions or comments that you may have.
Well, thank you, Nicole. So if there are any questions for Nicole, I think you should just at this point unmute yourself and ask the question so that you can have a good discussion.
So Nicole, what would we expect institutions to help? How do we expect them to do and to help this situation? What change?
Yeah, so institutions can help, for instance, with data sharing. And they can help with open access publishing or making it easier for researchers to share their research products. Penn State is actually doing that. So Penn State has Scholarsphere, which is a place where people can deposit data if they want to share. That's one place where you can share data. Penn State has agreements with some publishers so that they'll cover publication fees if you want to publish your papers open access. So there's some things institutions can do at that level. Some institutions are rethinking their promotion and tenure guidelines to recognize the work that is involved. So doing open science requires work, right? Because you have to put in the effort to share your data. You have to put in the effort to make your code usable by other people. It is an effort, right? And a lot of people see that as a barrier. Some places, some departments, some universities are starting to incorporate recognition of open science practices into their promotion and tenure guidelines, for instance. And so it's not something, because we're all very utilitarian, right? You're not going to do, if it only costs you and you don't get any benefit from it, it's a hard case to make. But if you can say, well, you share your data, oh, your institution will recognize that when you come up for tenure. Maybe they'll look at how many people have used the data that you've made publicly available, right? So there are things that you can do that the institutions are starting to do. Some, not all.
So what is the incentive for the researchers to embrace this open science?
Yeah, that's a really good question. So I'm not sure I have really good answers, but I'll do my best. So there's starting to be research on these things as well. And so there's a little bit of research evidence to show, for instance, that papers where if the data are shared, they get more citations. So that looks good for you as a researcher. Your paper gets cited more often. Data sharing papers, if it's a substantive enough data set, that in itself can become another paper. Okay, so that's an incentive there. If you write a really hefty piece of code, make it publicly available, that can be like, there's a Journal of Statistical Software, right? That's a place where we can publish that kind of thing and really lay it out. So there's sort of, that's the coin of the realm. There's those kinds of incentives. Another incentive, which I really like to kind of point out, because I think people don't necessarily think about this unless they've themselves been bitten, is that your most important collaborator is future you, right? So, and again, I'll speak from my own sad experiences of going back and looking at code that I've written, for instance, and then realizing I don't remember what I did anymore. I can't get it to work. And even if it does, I don't understand. And so if I annotate, if I make it clear, I have it all out there, then when I come back in 6 months or 7 months or a year, or somebody contacts me, 2 years later or 3 years later, and I don't have to say, oh, that grad student who worked on that project, she graduated and she's not in academia. I don't know how to get the code for you anymore. If it's all out there and documented, I spare myself that embarrassment, right? So I think there are some of those intangible things as well. One of my colleagues actually told a really nice story about this the other day, where it was some project that he had been working on, I don't know, maybe 8-10 years back, and it went into the file drawer, right? They never finished it. Maybe the student working on it moved on, but they had been very careful to document everything, as it turned out. And then, I don't know, one of his collaborators came by, popped up onto the scene because it was like a special issue of a journal, and he's like, oh, remember that project? Maybe we could get something together really quickly and easily, and if we revitalize it. And my colleague was like, oh, gee, I don't know, that was a long time ago. But he went back and he found that everything was very clearly documented and open. I think it was on GitHub even. So he was able to go back and basically revitalize this project that had been dormant for several years, and they got a publication out of it because it had been, and he's like, he was able to run the code, and it's like, oh yeah, oh right, okay, we can do this, right? And so again, if you think about it sort of selfishly, even from the perspective of future you, right? Do it for the sake of future you. Forget about the rest of the world.
Hi, this is Jason Liu from Bioinformatics Division. So, yeah, so in terms of essay statement, I'm not optimistic about its impact on the statistical practice. The reason is it only points problem. It does not provide a solution. Okay, some of the solutions proposed can in fact be far more dangerous than p-value. Okay, for example, the Bayesian factor, and it is notorious to depend on the price specification. In fact, I had a paper in the American Statistician, which shows very convincingly depends so strongly on the prior. So you can specify any prior, get whatever Bayesian factor you want. So I think some of the alternatives are far more dangerous than p-value. So that's the first point.
Yeah.
The second point is p-value can be a summary of the signal level in your study. For example, if it's null, we consider it's no signal. And then deviation from the null implies you have some signal that was further pursuing.
Yeah. Okay, yeah. So let me address the first point first. Yes, absolutely. So every method has its potential dangers. Certainly the dependence on the prior has been a critique of the Bayesian perspective. But again, I think if you are open about your choices and why you made the choices that you did, give the other, give the people reading your paper the full information, that can alleviate some of that. The prior shouldn't be hidden.
But can I just say, if you make a reporting of the study and interpretation of the study, it is so complicated. And then it's very hard for the scientific communication. We do have Bayesian procedure that's much more robust against the prior specification.
Right. No, there are definitely trade-offs there. I agree with you. That's something to definitely think about. As for the second, the p-value, so again, this statement is not saying do away with p-values. It's saying think about what they actually do measure. And you're right, it's a measure of compatibility, right? This is basically the first point. It's how incompatible the data are with your specified statistical model. And I think that's the point that you were making as well. So I don't disagree with that.
Yeah, can I also make a third point is I think the researcher must want to do good research and attach their reputation to a statement. Okay, so nowadays a lot of people, they just want to get anything published. So they do not really care about whether this will stand the test of time. So I think that's a big issue. Personally, when I submit a paper, I look at the result from all possible angles to make sure I'm satisfied. And so I think.
Yeah, I mean, unfortunately, as I'm sure you know, there's people need to publish. That's an incentive to slice things up into least publishable units, just so you get more papers out of the same. There's a lot of not great incentives out there right now, and that's part of what I think. Moslik was asking about institutional change. That's part of what I think needs to change as well to get beyond this.
Thank you.
Thank you.
Nico, there's a question in the chat window. Do you want me to?
Yeah, can I think? Okay. What do you think about some model where peer review, at least initially, is based on the introduction method section without the results included? Yeah. Oh, yeah. Would that reduce the incentive and importance of the p-value and thereby help this problem? Yeah, that's a great question and a great point. And in fact, this is what's called a registered report. So you can actually, there are some journals where you can do this now, and it's registered report. It's a little bit pre-registration. It's a little bit results blind. What is it called? Results blind acceptance. So there's different names for it. And yeah, that's exactly the idea, that you submit the introduction, you submit the plan, how you're going to collect the data and what you're going to do with the data. And then you get in principle acceptance once it's gone, that part has gone through peer review. And then if you do what you said you were going to do, then it doesn't matter how your results come out. That is a model that some journals are experimenting with. I don't know yet that it's prevalent enough or that to know whether it's successful or not, but in principle, yes, this should help with the problem, because then your ability to get your work published is not dependent anymore on whether the p-value you got was less than 0.05 or not, but it's going to be based on the merit of your ideas and the soundness of your data collection and your methods of analysis. Absolutely.
But can I just ask, will the publication depend on your finding? Suppose you have a significant finding, or you have no finding, does that make a
No.
difference?
No, if you collected the data the way you said you were going to and analyzed them the way that you said you were going to, then it does not matter what the results are.
So then we're getting to the e-life model.
Is that their model? I'm not familiar with them.
The e-life model basically says they're going to send out the papers for review, and it doesn't matter whether the reviewer says it's a great model or great paper or bad paper, they're going to just publish it anyway.
Oh, no. That's not how this works. You have to, so the method, the introduction, the methods and all of that part goes through peer review. And only if that is deemed to be acceptable, then you can go on and do your study and have it be published. So you'll get feedback on your method. So the paper could still get rejected if your experimental design, for instance, isn't sound enough, or if the analysis that you propose is not appropriate, the paper can still get rejected at that point.
So basically,
so then you don't waste your time. Then you don't go, at least with that journal, they won't publish it. Yeah.
Okay, yep.
We are running out of time, but I have one question that I wanted to ask. So you talked about the publications, we talked about the institutional change, and you did talk about little about the changes that the funding agencies are making in terms of needing data to be like having a policy about making data open and things like that. How does that has affect the or even the p-value discussion has affect how funding agencies are evaluating the proposals, or have they changed?
Yeah, I'm not sure it's really gotten to the funding agencies quite yet. Although, I mean, only in the sense that like NIH and NSF and some of these others like NASA now are starting to sort of require that things be made, data be shared, and that papers be published, open access. In terms of how they make their funding decisions, I'm not sure that they're quite there yet. I haven't seen it. They have, like NIH, for instance, now has a required rigor and reproducibility section in the grant proposals, but I think mostly, at least the limited view that I've seen, the experience that I have with a very few number of panels, is that basically comes down to what most people end up writing. We did a power analysis, and so that proves that we're being rigorous and reproducible. So that's not really it, right? Yeah.
Yeah, thank you.
Yeah.
Well, we're all
Over time.
Yeah. Thank you very much, Nicole. I appreciate all the great ideas that you shared with us, and of also taking time to talk to us.
No, thanks for coming. Thanks for having me. Bye.